We might go a little bit ahead this week. All right, so this first topic is interpreting a tree diagram. This section or this module is all about figuring out how many possible options there are. It's called the counting principle. So this one shows a tree diagram of choosing a president, vice president, treasurer. So there's two running for president. Okay, so Maria and Linda. And then there's three running for vice president. So if Maria's president, then John, Jim, or Bob could be vice president. Or if Linda's president, John, Jim, or Bob could be vice president. So it goes through all the possible different options. And you got two students running for treasurer. Okay, so this is all the different outcomes. So a tree diagram kind of breaks down and shows you all the possible outcomes. So the first question is, how many outcomes are there? You just count them. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 outcomes, okay? How many outcomes have both Maria and Jessica being chosen? So if I'm looking for Maria and Jessica, Maria, Jessica, 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 right? I wouldn't look at any of these down here because these down here are all Linda. So it would be 3 outcomes. How many outcomes do not have John being chosen? So do not have John being chosen would be, I guess you could just look at the list too. Anyone that doesn't have John in it, right? So there would be 8 of those. So you have 8 outcomes like that. So this one gives you all the list of combinations, but we obviously don't want to have to write out all those every single time. A tree diagram is nice because it shows us all of those, but we don't want to have to write out all those different combinations every time. So the way we can shortcut this is we can actually say, okay, to figure out how many possible outcomes there are, you would say there's what? 2 for president, 3 for vice president, and 2 for treasurer. Okay. What you can do is called the multiplication, or it's called the counting principle, is you can actually just do 2 times 3 times 2, and there are 12 outcomes. That'll tell you how many different outcomes are available for those. So that is the counting principle, which is the basis of what we're doing today. So this one right here, Tammy is ordering an ice cream dessert. She must order a size or a flavor of ice cream, a size, a flavor of ice cream, and a topping. So how many different outcomes could they create if there were 2 sizes, 4 flavors, and 1 topping to choose from? So you would just do 2 times 4 times 1, and there would be 8 different combinations. So she could actually go back there 8 different times and get a different combination every time that she goes. Okay. So you just multiply all the different combinations together, or the choices together, the outcomes together, and that will tell you how many different outcomes are possible. All right, this one, how many different kid lunches are possible? So it kind of gives you a chart. So you have 3 here, 2 here, 3 here, 1, 2, 3, 4 here, 1, 2, 3, 4, 5 here. So you would do 3 times 2 times 3 times 4 times 5, which is a big number, 360, I think. 20, 60, 120 times, 360 total different combinations, okay? So you just multiply all the numbers together to figure out the different outcomes. The joke here, or I guess not the joke, but the ha-ha. If you think about your closet with your shirts, let's say in your shirts you have 8 shirts. And your pants, you have, 6 pants. And your shoes, you have 4 pairs of shoes. If you do that, 8 times 6 times 4, what is that, 48 times 4? Yeah, solve it for me. 192, okay? So you could go 192 days and never wear the same outfit. That's a half a year. So with just 8 shirts, 6 pants, and 4 pairs of shoes, you could create 192 over 6 months worth of different outfits. So my wife doesn't like when she goes to the closet and says she doesn't have anything to wear. And I said, look, no, you got 192 possibilities with just 8 shirts and 6 pants and 4 shoes. And of course, the female response to that usually is, well, they all don't match. Yes, they do. There's a top, a middle, and a bottom. They all match. They all fit you. All right. Oops, I didn't mean to put that there. There's a lot of different things you can do there, like with that, though, and I won't go into too many of them, but we can talk about a couple of them just for a second because this will go quick. We only got like one more topic really to talk about. Like license plates numbers. Like you think about how many different license plate numbers they could create. So there's 26 letters and there's 10 numbers because you can use 0 through 9, right? Actually, do you know why? So there's 10 numbers. And I actually don't remember this. Someone actually has told me this in class. Plus 26. That's 36 different combinations you could use on a license plate, like in the one digit, right? Do you know why it's actually only 35? Does anybody know? I was doing this in class, and somebody told me that I was wrong. So 0 and O, you cannot use one of them. I don't know which one, but you can't have a 0 or you can't have like an O because it looks like a 0. So there's actually only 35 combinations you can use. So if you just did a 6-digit license plate, that's 1, 2, 3, 4, 5, 6. You can do 35 to the 6 too. You create 1.8 billion different combinations of just license plate. And that's just using 6. I mean, I know some of them have 5, some of them have whatever different ones. You got different states like that. So they obviously have enough creation there. If you do credit cards, how many different digits can go on the first digit of the credit card? 10, right? 0 through 9 could be the first digit of the credit card. So there's 10 of those. And how many digit long is a credit card? 16, right? So it's 10 to the 16th power. That is a million, billion, trillion, 10 quadrillion different credit card options that are optioned. But then they added the CVV code, which has like 3, right? And then if you take it times 12 for the month, and I think it goes out like 5 years for the expiration date, you make 600 quintillion different credit card options. What's crazy about this, and this is way outdated, but like those programs, the programs that can like run through all those different options is like seconds, like milliseconds basically. The computer program can just go through it. I believe I read this stat like, it's probably like 6 years ago now. The FBI could do all 600 quintillion in like less than 6 seconds. So like now I'm sure it's like literally milliseconds that they can go through that. So that's like internet security has to be able to kick people out that fast. Okay, let's go to the next topic. All right, so the next main topic, which is all the only thing that's left in this section is short, so we probably will jump to the next one for a few minutes. Permutation and combination. So let me talk about these for a second. This is a formula. We do not do the formula in the class. The calculator does it for us. I believe this possibly is even on like our phones. So permutation is you use it when the order matters. And combination, use it when the order does not matter. Okay. So first of all, when do you use permutation or combination? We use both of these to find when you're given a total amount and then you're choosing a certain amount out of that. So this one has like 2 numbers that you're dealing with. So if there's 20 of y'all in here and I wanted 3 of you to come work a problem on the board, how many different combinations could I create? How likely are you to be picked if I did that? If there's 20 total and I'm going to pick 3 out of that, okay? So when you're given like 2 numbers, a given amount, and you're choosing a certain amount out of that, use that. So the permutation, the order matters. The combination, the order does not matter. So for example, I should arrange this a little better. So we use this. All right, so permutation, the order matters. So things like a race. First place is better than second place is better than third place. If you had 20 people racing, you want to figure out how many different combinations they could finish third. A race, the president, vice president, secretary, like we just did. That one is one that president's better than vice president, better than secretary. That matters. I'm trying to think of Different examples that they use: president, VP, secretary, like the order matters there. Travel is one, the weird one that they use. Like if I was traveling to different cities, the order does matter, right? If I had to go to Miami and Daytona today, I don't want to go to Miami then Daytona. I'd want to go to Daytona then Miami. So like order matters when you travel. Anything that says anything about ranking, like if you're ranking sales associates and things like that, like the order matters. Combination, the order does not matter. So like if I had a menu of 12 appetizers and I got to choose 3 of them, like the order doesn't matter that they come on my plate. This is hard to think of an example because the order doesn't matter most of the time. Okay. I'll come back to one. Maybe I'll write some more in just a second. Do you think you get more possibilities when the order matters or when the order doesn't matter? When it doesn't matter is the common thought process here, right? You think you get more when the order doesn't matter. Okay, this is a silly example, but take a BLT. If I make a BLT, that's one sandwich, right? A bacon, lettuce, tomato, right? Well, what if that's just one sandwich? It doesn't really matter if it comes tomato, lettuce, bacon, or bacon, lettuce, tomato, or whatever. But what if you have picky people? If you have picky people, a bacon, lettuce, tomato may be different than a bacon, tomato, lettuce, or tomato, bacon, lettuce, or tomato, lettuce, bacon, or what else? I got some more combinations here. Lettuce, bacon, LBT, LTB, okay? So if you had 6 really picky people, they'd be like, no, that's not a true BLT unless you do tomato, bacon, and then lettuce, okay? So when the order matters, it creates more individual options. Okay, so that's why it makes sense. I guess I have small children, so I think about this. Y'all know this because of percentiles. But like, if I lined y'all up, that's one line of my students. But if y'all fought over who was line leader, then to you in your brain, it's different groups. Like it's a different line if you get to be line leader versus he gets to be line leader versus whatever. So when the order matters, it actually creates different opportunities here. All right. How do we do these problems? So first of all, that's the first decision. On the first topic, maybe even the first 2 topic, it flat out tells you how many ways can this be done if the order of the choices matter. Okay. So if the order matters, we are going to do permutation. So it says we'll choose 2 colors out of 4 different colors. On the calculator, they have these buttons, the NPR and NCR. If you click on explanation, it's going to show you how to do it by hand with the formula. We do not have to do it by hand. We can use these buttons right here. So if the order matters, I'm going to do the bigger number first and then the permutation 2. Okay? In 4P2 is 12. Okay? And then same thing if on B, if the order doesn't matter, I do the bigger number first and then 4C2. What is that one? That one's 6. I'll leave that on the calculator here, so we'll write this, okay? So this does do it in the calculator for us. You just have to determine if the order matters or not. So this is 6. This one is 4P2, and it was 12. And this one was 4C2, and it was 6. And use the buttons on the calculator. All right, so this one still tells you whether the order matters or not. You have 5. You want to choose 5 objects without replacement. All of these are going to be without replacement. Replacement means that you put it back in. Like if I had a deck of cards, if I drew a card out, do I put it back in for the next time I draw or not? So you got 15. In order of choices, how many if the order does not matter? So again, this one tells you whether the order matters or not. 15C5 is 3003. And then permutation 15P5, 360360. So these first two are super easy because they just tell you whether the order matters or not. The last one does not tell you whether the order matters or not. This was what? 15P5. My other one was 15C5. All right, so the first two, super easy. Probably could delete one of those topics even because they're kind of the same. What happens if it does not tell you whether the order matters or not, you just have to pick. So a certain committee consists of 18 people from a committee of president, vice president, treasurer are to be chosen. And how many ways can the three be chosen? So I kind of mentioned this already, but president is better than vice president is better than secretary. So we are going to use the P for this one. Okay, so that is 4896. Pizza parlor has a choice of 11 toppings for its pizza. From these 11 toppings, how many different 7-topping pizzas can you create? A pizza does not matter which order you put the toppings on, all right? So you would use combination for that one. Okay, so you just have to decide, does the order matter or does it not? So order matters. So you use 18P3. Order does not matter. So you use 11C7. That's like all that's in this section. So we're definitely jumping to the next section. I got to go a little longer than 10 minutes. 15, however long it's been. Let's look at one more just to make sure. 59 athletes are running a race. The gold medal is to be given a winner. Silver medal is to be given second, and bronze third. How many different ways could you finish the three? So this would be 59. The order does matter. First place is better than second, better than third. So 59P3, which is a big number, 195,054. To log on to a certain computer account, the user must type in a 3-letter password. In such a password, no letters may be repeated. Only the lowercase letter may be used. Such 3-letter password. How many such 3-letter password patterns are possible? 26 letters in the alphabet. So 26. The order does matter on this because you're talking about a password. Okay, we'll double check it, but on that one, so it's not always going to be permutation and combination on each one. They both could be permutation. They both could be combination. I wasn't going to write this out, but since that password one we didn't have listed up there. So this one was 59P3, and this one was 26P3. Order matters, order matters. So the only thing you need to do is figure out whether the order matters or does not. All right.